The universe is a stage, and gravity and light are its principal performers. Picture a star's light bending around a massive galaxy, or the invisible pull of gravity sculpting entire clusters of stars into swirling galaxies. These two forces, gravity, the silent architect, and light, the radiant messenger, work in tandem to shape the cosmos in ways that defy imagination. But how do they collaborate to create the reality we perceive? Today, we'll explore this celestial dance, uncovering how gravity's invisible embrace and light's luminous reach intertwine to craft the universe as we know it. From the bending of starlight to the birth of galaxies, this journey will reveal the profound partnership between these cosmic forces and how they shape the very fabric of existence. Get ready to see the universe in a whole new light. Gravity and light are more than just forces, they are the architects of the cosmos, shaping everything from the tiniest particles to the grandest galaxies. Imagine gravity as the invisible sculptor, tirelessly molding the universe's vast structures. It's the force that pulls gas and dust together, igniting the birth of stars, and binds planets into their orbits. Without gravity, the universe would be a formless void, a chaotic sea of matter drifting aimlessly through space. But gravity doesn't work alone. Light, its luminous counterpart, is the universe's storyteller, carrying the secrets of distant stars and galaxies across billions of light years. It's through light that we glimpse the beauty of nebulae, the fiery hearts of stars, and the intricate dance of galaxies. Together, these two forces create a symphony of cosmic proportions. Gravity bends the fabric of spacetime, and light travels along these curved paths, revealing the hidden architecture of the universe. This collaboration isn't just a coincidence, it's a partnership that defines the very nature of reality. For instance, when light from a distant star passes near a massive object like a galaxy, gravity bends its path, creating stunning phenomena like gravitational lensing. This bending of light not only magnifies distant objects, but also allows us to peer deeper into the cosmos than ever before. It's as if gravity is the artist and light is the paintbrush, together crafting the masterpiece we call the universe. But how did we come to understand this intricate relationship? The story begins with groundbreaking discoveries that first revealed the interplay between gravity and light. From Einstein's theory of general relativity to the observations of distant quasars, humanity's journey to unravel this cosmic dance has been nothing short of extraordinary. And as we delve deeper into these revelations, we'll uncover how these two forces continue to shape our understanding of the universe in ways that are both profound and awe-inspiring. The story of gravity and light begins not in the vast expanse of space, but in the minds of some of history's greatest thinkers. Isaac Newton, with his groundbreaking laws of motion and universal gravitation, laid the foundation for our understanding of gravity. He described it as a force that pulls objects toward one another, governing everything from the fall of an apple to the orbit of planets. His work was revolutionary, but it was only the beginning. Newton's laws couldn't fully explain the peculiar behavior of light or how gravity might influence it. That mystery would remain unsolved for centuries, waiting for another genius to step forward. Enter Albert Einstein. In 1915, Einstein introduced his theory of general relativity, a radical reimagining of gravity itself. Instead of a force, Einstein proposed that gravity is the result of massive objects warping the fabric of spacetime. Imagine placing a bowling ball on a trampoline. The surface bends, creating a curve. Now, picture spacetime as that trampoline, and planets, stars, and galaxies as the bowling balls. Light, Einstein suggested, travels along these curves, bending as it moves through the warped spacetime. This was a revelation. Gravity didn't just pull objects, it shaped the very paths that light could take. But theory alone wasn't enough. The world needed proof, and it came in 1919 during a total solar eclipse. Sir Arthur Eddington led an expedition to observe the eclipse, capturing images of stars near the sun. According to Einstein's predictions, the sun's gravity would bend the light from these stars, making them appear slightly out of place. When the results were analyzed, they matched Einstein's calculations almost perfectly. The scientific community was stunned. This wasn't just a win for Einstein, it was a triumph for humanity's ability to unravel the secrets of the cosmos. For the first time, we had tangible evidence that gravity and light were deeply intertwined, partners in a cosmic dance that shapes the universe. These historical milestones weren't just academic exercises, they were leaps forward in our understanding of reality. Newton gave us the tools to describe gravity's effects, and Einstein showed us how it bends the very fabric of existence. Together, their discoveries paved the way for the modern tools and technologies that let us observe this dance in action. From the earliest equations to the most advanced telescopes, each step in this journey brings us closer to understanding the universe's grand design. And as we'll soon see, the story doesn't end there, it's still being written, with new chapters unfolding every day. Modern observatories are like the eyes of humanity, gazing deep into the cosmos to witness the celestial dance of gravity and light in breathtaking detail. Among these, the Hubble Space Telescope stands as a pioneer, capturing images that have transformed our understanding of the universe. Since its launch in 1990, Hubble has peered into the farthest reaches of space, revealing galaxies billions of light years away and showcasing the intricate ways gravity shapes their light. But Hubble was just the beginning. Enter the James Webb Space Telescope, launched in 2021, a technological marvel designed to see even further and with greater precision. Together, these observatories act as cosmic detectives, uncovering the hidden interplay between gravity and light in ways we could only dream of a century ago. One of the most fascinating phenomena these telescopes have revealed is gravitational lensing, a cosmic illusion where massive objects, like galaxies or black holes, bend the light from objects behind them. It's as if the universe itself is a giant magnifying glass, using gravity to distort and amplify the light of distant galaxies. Hubble has captured countless examples of this, showing distant galaxies stretched into arcs and rings around foreground objects. But with James Webb's infrared capabilities, we're now seeing even more. This telescope can peer through cosmic dust and gas, revealing the faintest details of lensed galaxies that were previously invisible. These observations don't just dazzle us with their beauty, they challenge our understanding of reality itself. For instance, gravitational lensing allows us to see galaxies that existed just a few 100 million years after the Big Bang. These ancient structures, magnified by the gravity of intervening galaxy clusters, offer a glimpse into the universe's infancy, but they also raise profound questions. How did galaxies form so quickly after the birth of the cosmos? What role did dark matter, the invisible substance that makes up most of the universe's mass, play in shaping these early structures? Each image from these observatories is a puzzle piece, helping us piece together the story of how the universe evolved. Beyond lensing, these telescopes have also captured the dynamic interplay of gravity and light in other ways. Hubble has observed stars being torn apart by the immense gravity of black holes, their light flaring brightly before fading into oblivion. James Webb, with its ability to see in infrared, has revealed the birth of stars within dense clouds of gas and dust, where gravity pulls matter together until it ignites into stellar fire. These observations aren't just scientific data, they're snapshots of the universe's ongoing creation, moments frozen in time that tell the story of how gravity and light shape everything we see. Yet, with every discovery comes new mysteries. The more we learn, the more we realize how much we don't know. Why does dark energy, the mysterious force driving the universe's accelerated expansion, seem to counteract gravity on cosmic scales? How do black holes, with their unimaginable gravitational pull, influence the light and matter around them in ways we're only beginning to understand? These questions remind us that the universe is far more complex and far more wondrous than we ever imagined. As we continue to explore the cosmos with these incredible tools, one thing becomes clear: gravity and light aren't just forces or phenomena. They're the threads that weave the tapestry of reality. And with each new observation, we're not just peering into the past, we're uncovering the secrets of the universe's future. The dance continues, and with every step, we're learning to move in rhythm with the cosmos. Imagine looking through a magnifying glass and seeing not just one image, but 4 or even more. This isn't science fiction, it's gravitational lensing, one of the most extraordinary phenomena in the universe. At its core, gravitational lensing occurs when a massive object, like a galaxy or a cluster of galaxies, bends the light from an object behind it. This cosmic distortion works much like a magnifying glass, warping and amplifying the light to create stunning visual effects. One of the most famous examples is the Einstein cross, a quasar whose light is bent and split into 4 distinct images by the gravity of a foreground galaxy. It's as if the universe is playing a game of cosmic mirrors, reflecting and reshaping reality in ways that challenge our understanding. But how does this bending of light happen? Picture spacetime as a vast, stretchy fabric. When a massive object like a galaxy cluster sits on this fabric, it creates a deep curve. Light traveling near this curve doesn't move in a straight line. Instead, it follows the contours of the warped spacetime, bending around the massive object. This bending can produce multiple images of the same distant object, or even stretch it into arcs and rings. The Hubble Space Telescope has captured countless examples of this, revealing galaxies twisted into surreal shapes by the gravitational pull of foreground clusters. These images aren't just beautiful, they're windows into the hidden architecture of the cosmos. One of the most breathtaking demonstrations of gravitational lensing is the Hubble Deep Field. In this iconic image, a galaxy cluster in the foreground acts as a natural telescope, magnifying the light of galaxies billions of light years behind it. These distant galaxies, some of the earliest ever observed, appear as faint smudges of light, stretched and distorted by the cluster's immense gravity. Without gravitational lensing, many of these ancient galaxies would remain invisible to us, their light too faint to detect. It's as if the universe is giving us a helping hand, using its own gravity to reveal its deepest secrets. But gravitational lensing isn't just a cosmic curiosity, it's a powerful tool for science. By studying how light bends around massive objects, astronomers can map the distribution of dark matter, the invisible substance that makes up most of the universe's mass. Dark matter doesn't emit or absorb light, making it impossible to see directly, yet its gravitational effects are undeniable. When light from a distant galaxy bends more than expected, it's a clear sign that dark matter is at work, shaping the path of light in ways that visible matter alone cannot explain. This makes gravitational lensing one of our most important tools for uncovering the invisible structure of the universe. Consider the bullet cluster, a pair of colliding galaxy clusters that provided some of the first direct evidence for dark matter. As the clusters collided, their hot gas slowed down, while their dark matter passed right through, leaving a distinct separation between the visible and invisible components. Gravitational lensing revealed this separation, showing us where the dark matter was concentrated. It was a groundbreaking discovery, offering a glimpse into the hidden scaffolding that holds the universe together. As we continue to explore the cosmos, gravitational lensing remains a key to unlocking its deepest mysteries. From revealing the earliest galaxies to mapping the invisible web of dark matter, this phenomenon is reshaping our understanding of the universe. And with every new observation, we're reminded that the cosmos is far stranger and far more beautiful than we ever imagined. The dance of gravity and light continues to unfold, and with each step, we're learning to see the universe in a whole new way. While gravity and light are the visible stars of the cosmic dance, there's another player in this grand performance, one we can't see, but whose presence is undeniable. Dark matter, the universe's invisible partner, shapes the very fabric of reality, even though it emits no light and remains hidden from our telescopes. Imagine a stage where the actors are cloaked, yet their movements dictate the entire performance. That's dark matter, a mysterious substance that makes up about 85% of all matter in the universe, silently guiding the formation of galaxies, clusters, and the cosmic web itself. So how do we know dark matter exists if we can't see it? The answer lies in its gravitational influence. When astronomers observe galaxies, they notice something peculiar. The stars on the outer edges move much faster than they should based on the visible matter alone. According to the laws of gravity, these stars should drift away, yet they stay bound to their galaxies. This discrepancy points to an invisible force, dark matter, whose gravity holds everything together. It's like a cosmic glue, invisible to our eyes but essential to the universe's structure. But dark matter's influence doesn't stop there. Its gravitational pull also bends light, a phenomenon we see in gravitational lensing. When light from a distant galaxy passes through a region rich in dark matter, its path curves, creating distorted or magnified images. These distortions act as cosmic fingerprints, revealing where dark matter is concentrated. For instance, the bullet cluster, a collision of two galaxy clusters, provided some of the most compelling evidence for dark matter. While the visible gas from the collision slowed down, the gravitational lensing effect showed that the majority of the mass, dark matter, had passed right through unaffected. This observation was a turning point, confirming that dark matter isn't just a hypothesis, it's a fundamental part of our universe. What exactly is dark matter? That's one of the biggest questions in modern science. While we don't yet know its true nature, scientists have proposed several theories. One leading idea is that dark matter is made up of weakly interacting massive particles, or WIMP hypothetical particles that rarely interact with ordinary matter except through gravity. Another possibility is that dark matter consists of actions, ultra-light particles that could permeate the cosmos. Despite decades of research, dark matter has eluded direct detection, making it one of the most tantalizing mysteries in physics. As if dark matter weren't mysterious enough, its counterpart, dark energy, adds another layer of intrigue. While dark matter pulls the universe together with its gravity, dark energy pushes it apart, driving the accelerated expansion of the cosmos. Together, these two unseen forces shape the universe's destiny, balancing each other in a cosmic tug of war. And yet, despite their profound influence, we know even less about dark energy than we do about dark matter. It's a reminder that the universe is still full of secrets, waiting to be uncovered. The story of dark matter and its role in the cosmic dance is far from complete. Every observation, every experiment brings us closer to understanding this invisible force that shapes the universe. And as we continue to explore, we're reminded that the cosmos is far more complex and far more wondrous than we ever imagined. The dance of gravity and light may be dazzling, but it's the unseen partner, dark matter, that holds the stage together, guiding the universe's grand performance. While dark matter pulls the cosmos together, there's another unseen force at work, one that's pushing the universe apart at an ever-increasing rate. This mysterious force is dark energy, and it's reshaping our understanding of the universe's destiny. Unlike gravity, which draws objects closer, dark energy acts as a kind of cosmic repulsion, stretching the fabric of spacetime itself. It's as if the universe has an invisible hand, gently, but relentlessly pushing galaxies away from each other, accelerating the expansion of everything we see. The discovery of dark energy came as a surprise, even to astronomers. In the late 1990s, two teams of researchers were studying distant supernovae, the explosive deaths of massive stars, to measure how fast the universe was expanding. They expected to find that the expansion was slowing down, pulled by gravity over billions of years. Instead, they discovered the opposite. The universe wasn't just expanding, it was speeding up. This shocking revelation earned the teams the Nobel Prize in Physics in 2011 and opened a new chapter in our understanding of the cosmos. But how do we know dark energy is responsible for this acceleration? One clue comes from the cosmic microwave background, the faint afterglow of the Big Bang. This ancient light, which fills the entire universe, carries imprints of the early cosmos, including the seeds of galaxies and the distribution of matter. By studying these imprints, scientists can measure the universe's expansion rate and infer the presence of dark energy. The data shows that dark energy makes up about 68% of the universe's total energy, dwarfing even dark matter. Together, these two invisible forces, dark matter pulling and dark energy pushing, shape the universe's evolution in ways we're only beginning to understand. But what does this mean for the future of the cosmos? If dark energy continues to dominate, the universe's expansion will keep accelerating, pulling galaxies further and further apart. Over billions of years, distant galaxies will fade from view, their light stretched into invisibility by the relentless expansion. Eventually, the universe could become a vast, cold, and lonely place, with galaxies isolated in an ever-expanding void. This scenario, known as the Big Freeze, is one of several possible futures, but it's the one most supported by current observations. It's a sobering thought, yet also a reminder of how dynamic and ever-changing the universe truly is. While dark energy points us toward the future, gravity and light continue to reveal the universe's past. By observing the bending of light around massive objects, we can trace the distribution of matter billions of years ago, mapping the cosmic web as it formed. These observations give us a glimpse into the early universe, showing how gravity sculpted the first galaxies and clusters. Meanwhile, light from distant supernovae and quasars carries echoes of a younger cosmos, allowing us to piece together the story of how the universe evolved. It's a story that's still being written, with dark energy playing a pivotal role. The interplay between gravity, light, dark matter, and dark energy is a cosmic dance unlike any other. Each force has its part to play, shaping the universe in ways that are both profound and mysterious. As we continue to explore these forces, we're not just learning about the cosmos, we're learning about ourselves and our place within it. The universe is a stage, and these invisible actors are the ones guiding its grand performance. And as we watch this dance unfold, we're reminded that there's still so much to discover, so many secrets waiting to be uncovered. The cosmic microwave background, or CMB, is like a time capsule from the dawn of the universe, a faint whisper of light that has traveled billions of years to reach us. This afterglow, a remnant of the Big Bang, is the oldest light we can observe, dating back to when the universe was just 380,000 years old. Imagine the cosmos as a newborn, glowing with energy, but still too hot and dense for light to travel freely. As the universe expanded and cooled, protons and electrons combined to form neutral atoms, allowing light to break free and travel across space. This moment of liberation is what we now see as the CMB, a snapshot of the universe in its infancy. But the CMB isn't just a relic of the past. It's a treasure trove of information about how gravity and light shaped the early cosmos. In those first moments, tiny fluctuations in density, caused by gravity's pull, created ripples in the fabric of the universe. These ripples, imprinted in the CMB, are the seeds of everything we see today: galaxies, stars, and even planets. Light, carrying these imprints, began its journey across the cosmos, bending and shifting as it encountered the gravitational influence of matter. This interplay between gravity and light didn't just create the CMB, it set the stage for the universe's evolution. One of the most remarkable features of the CMB is its incredible uniformity. No matter where you look in the sky, the temperature of this ancient radiation is almost exactly the same, just a few degrees above absolute zero. But within that uniformity lie tiny variations, fluctuations so small they are measured in millionths of a degree. These variations are the fingerprints of gravity's early work, the subtle differences in density that would eventually grow into the vast structures we see today. It's as if the universe left us a blueprint, a map of its beginnings that we're still learning to read. Modern instruments like the Planck satellite have captured the CMB in unprecedented detail, revealing patterns that tell the story of the universe's first moments. These patterns aren't random, they're the result of gravity pulling matter together, creating regions of slightly higher density. Over billions of years, these regions grew into the galaxies and galaxy clusters we observe today. By studying the CMB, we can trace the universe's growth from a hot, dense soup of particles to the intricate web of galaxies that fill the cosmos. The CMB also offers clues about the universe's composition, including the elusive dark matter and dark energy. The way light bends and shifts as it travels through the cosmos is influenced by these invisible forces, leaving subtle imprints in the CMB's patterns. For example, the distribution of temperature fluctuations tells us how much dark matter was present in the early universe, while the overall shape of the CMB helps us measure the effects of dark energy. It's a cosmic detective story, with the CMB as our most important piece of evidence. As we continue to study the CMB, we're not just looking back in time, we're uncovering the universe's story, from its fiery birth to its present-day complexity. This ancient light, a testament to the interplay of gravity and light, reminds us that the cosmos is a dynamic, ever-changing place, and with each new observation, we're piecing together the puzzle of how the universe began, how it evolved, and where it might be headed. The CMB is more than a snapshot. It's a window into the very fabric of reality, inviting us to explore the mysteries of the cosmos. Galaxies are the universe's grandest masterpieces, vast collections of stars, gas and dust held together by the invisible hand of gravity. Every galaxy, from the spiraling arms of the Milky Way to the elliptical giants floating in deep space, owes its existence to this fundamental force. Gravity is the cosmic sculptor, pulling together clouds of gas and dust over billions of years, compressing them until they ignite into stars and galaxies. But gravity doesn't work in isolation. Light plays a critical role, too. It's through light that we see the intricate details of galaxies, from their swirling arms to their glowing cores. Together, gravity and light reveal the story of how galaxies are born, evolve, and shape the cosmos. At the heart of every galaxy lies a mystery, a supermassive black hole, an object so dense and massive that its gravity bends space-time to the breaking point. These cosmic behemoths, millions or even billions of times the mass of our Sun, reside in the centers of galaxies, exerting an immense influence on their surroundings. Imagine a whirlpool in the ocean, pulling everything toward its center. This is what a supermassive black hole does to the stars, gas, and dust around it. Yet, despite their destructive potential, these black holes are also creators. Their gravity can trigger the formation of new stars, while the intense energy they release can shape entire galaxies, carving out vast regions of space and influencing how galaxies grow and evolve. But how do we know these black holes exist if they're invisible? The answer lies in the light emitted by the materials swirling around them. As gas and dust fall toward a black hole, they form an accretion disk, a glowing ring of superheated matter that radiates light across the spectrum. This light reveals not only the presence of the black hole, but also its immense gravitational pull. In some cases, black holes spew out jets of particles and radiation at nearly the speed of light, creating some of the most energetic phenomena in the universe. These jets can stretch for thousands of light years, illuminating the galaxy and beyond. It's a stunning reminder of how gravity and light work together to shape the cosmos. While supermassive black holes dominate the centers of galaxies, the stars orbiting them tell a story of their own. Stars are born from the same clouds of gas and dust that form galaxies, ignited by gravity's relentless pull. Over millions of years, gravity compresses these clouds until they reach the critical temperature and pressure needed for nuclear fusion to begin. At that moment, a star is born and light floods into the cosmos. But gravity doesn't stop there. It continues to shape the star's life, from its fiery youth to its eventual demise. For stars like our Sun, this journey ends in a gentle puff of gas, leaving behind a glowing remnant called a white dwarf. For more massive stars, the end is far more dramatic, a supernova explosion that scatters elements across the galaxy, seeding the next generation of stars and planets. These life cycles of stars are a testament to the delicate balance between gravity and light. Without gravity, stars would never form, and without light, we would never see them. Together, these forces create the beauty and complexity of galaxies, from the swirling arms of spirals to the dense cores of ellipticals. And as we continue to explore the cosmos, we're learning how galaxies grow, evolve, and interact in a cosmic dance that spans billions of years. The story of galaxies is far from over. With every new observation, we uncover more about how gravity and light shape these vast structures, from their earliest beginnings to their ultimate fate. Whether it's the birth of stars, the power of supermassive black holes, or the intricate dance of galaxies in clusters, the universe is a stage where gravity and light perform in perfect harmony. And as we watch this cosmic ballet unfold, we're reminded of the profound partnership that shapes everything we see. and everything we've yet to discover. Every star in the night sky has a story, a journey that begins in the darkest corners of the cosmos and ends in a blaze of glory. This journey, known as stellar evolution, is a tale of gravity and light working in perfect harmony, or sometimes in dramatic conflict. It all starts in the heart of a dense molecular cloud, where gas and dust swirl in a cosmic dance. Gravity, ever the patient sculptor, begins to pull these particles together, compressing them into a dense core. Over thousands of years, this core grows hotter and denser until, finally, the pressure triggers nuclear fusion. At that moment, a star is born and light floods into the universe for the first time. But this is just the beginning. For most of its life, a star exists in a delicate balance between the inward pull of gravity and the outward pressure of light and heat. Gravity keeps the star from flying apart, while the energy generated by fusion pushes back, creating a stable, glowing sphere. Take our sun, for example. It's been burning for about 4.5 billion years, converting hydrogen into helium at its core, and it has billions of years left before it exhausts its fuel. This equilibrium, known as hydrostatic equilibrium, is what allows stars to shine steadily for so long, bathing their planets in light and warmth. Not all stars, however, are destined for such a quiet existence. The fate of a star depends largely on its mass. Smaller stars, like red dwarfs, burn their fuel slowly and can live for trillions of years, quietly fading into darkness. But for more massive stars, the story is far more dramatic. As they burn through their hydrogen, they begin to fuse heavier elements like helium, carbon, and oxygen in their cores. Each new stage of fusion releases even more energy, causing the star to swell into a red giant or supergiant. These colossal stars shine with incredible brightness, but their lives are short-lived, lasting only a few million years. The end of a massive star's life is one of the most spectacular events in the universe, a supernova. When these stars can no longer sustain fusion, their cores collapse under gravity's relentless pull. In a fraction of a second, the core rebounds, sending a shockwave through the star that tears it apart in a blinding explosion. For a brief moment, the supernova outshines an entire galaxy, releasing more energy than the sun will in its entire lifetime. But the true legacy of a supernova lies in what it leaves behind. The explosion scatters heavy elements like iron, gold, and uranium across space, seeding the cosmos with the building blocks of planets and even life itself. What remains after a supernova depends on the star's initial mass. For some, the core collapses into a neutron star, an object so dense that a teaspoon of its material would weigh billions of tons. Neutron stars spin rapidly, emitting beams of light that sweep across the cosmos like a cosmic lighthouse. These pulsars are some of the most precise clocks in the universe, their pulses so regular they rival atomic clocks on Earth. For the most massive stars, the core continues to collapse until it forms a black hole, an object with gravity so strong that not even light can escape. The life and death of stars are not just isolated events, they are the driving force behind the evolution of the universe. The heavy elements forged in stellar cores and scattered by supernova are the raw materials for new stars, planets, and even life. Every atom in your body, from the calcium in your bones to the iron in your blood, was once part of a star that lived and died billions of years ago. In this way, stars are not just celestial objects, they are the architects of the cosmos, shaping the universe with every stage of their existence. From the birth of a star in a molecular cloud to the explosive brilliance of a supernova, The story of stellar evolution is a testament to the power of gravity and light. These forces don't just shape stars, they shape us, connecting us to the cosmos in ways that are both profound and humbling. As we gaze at the night sky, we're not just looking at distant points of light, we're witnessing the ongoing story of creation, a story in which we, too, are a part. And with every new discovery, we're reminded that the universe is not just a place of stars, it's a place of endless wonder. When gravity reaches its most extreme, the universe reveals some of its most fascinating and bizarre creations: neutron stars and black holes. These objects are born from the deaths of massive stars, where gravity's pull becomes so overwhelming that it overcomes every other force in nature. Picture a star many times more massive than our Sun reaching the end of its life. After burning through its fuel and undergoing a cataclysmic supernova explosion, the core collapses under its own weight. If the remaining core is between about 1.5 to 3 times the mass of the Sun, it doesn't stop collapsing until it forms a neutron star, a city-sized object so dense that a single teaspoon of its material would weigh billions of tons. But if the core is even more massive, gravity's grip becomes unstoppable, crushing it into a black hole where not even light can escape. Neutron stars are like cosmic diamonds, incredibly dense and spinning at astonishing speeds. Some of these stars, called pulsars, emit beams of light from their magnetic poles. As they rotate, these beams sweep across the cosmos like a lighthouse, appearing to pulse when observed from Earth. Pulsars are some of the most precise clocks in the universe, with some rotating hundreds of times per second. Their regularity has made them invaluable tools for testing the laws of physics, including Einstein's theory of general relativity. But neutron stars aren't just cosmic timekeepers, they're also laboratories for studying matter under extreme conditions. The intense gravity and magnetic fields on their surfaces create environments unlike anything we can replicate on Earth, offering insights into the fundamental nature of matter itself. Black holes, on the other hand, are gravity's ultimate triumph. These enigmatic objects are so dense that they warp spacetime to the point of no return, creating a boundary called the event horizon. Once anything crosses this boundary, whether it's matter, light, or even time itself, it can never escape. For decades, black holes existed only in theory, but in 2019, the Event Horizon Telescope collaboration captured the first ever image of a black hole's event horizon. Located in the center of the galaxy Messier 87, this black hole's silhouette, surrounded by a glowing ring of light, confirmed what Einstein's equations had predicted over a century earlier. It was a monumental achievement, offering humanity its first direct glimpse into the heart of one of the universe's most mysterious objects. But black holes aren't just cosmic vacuum cleaners, they're active, dynamic forces that shape their surroundings. Supermassive black holes, which reside at the centers of galaxies, can influence the growth and evolution of entire galaxies. As matter falls into these black holes, it heats up and emits intense radiation, sometimes forming glowing disks of gas and dust called accretion disks. In some cases, black holes launch jets of particles and energy at nearly the speed of light, carving out vast regions of space and influencing the formation of stars and galaxies. These jets can stretch for thousands of light years, illuminating the cosmos with their brilliance. The study of neutron stars and black holes isn't just about understanding extreme gravity. It's about uncovering the universe's deepest secrets. By observing these objects, we're learning how matter behaves under conditions we can't replicate on Earth, testing the limits of our physical theories, and exploring the boundaries of spacetime itself. These cosmic extremes challenge our understanding of reality, offering glimpses into the universe's most fundamental processes. And as we continue to explore, we're reminded that the universe is far stranger and far more wondrous than we ever imagined. The dance of gravity and light takes on a new intensity in these objects, revealing the universe's most dramatic performances. As matter spirals toward a black hole or neutron star, it doesn't just vanish into the void, it puts on one of the most dazzling shows in the universe. This cosmic spectacle is powered by something called an accretion disk, a glowing ring of superheated gas and dust that forms as material falls inward, trapped by the immense gravitational pull of these extreme objects. Picture a whirlpool of light, spinning faster and faster as it gets closer to the center, heating up until it glows with the energy of billions of stars. This is the heart of some of the brightest and most energetic phenomena in the cosmos, and it all begins with the relentless tug of gravity. When matter gets too close to a black hole or neutron star, it doesn't fall straight in. Instead, it begins to orbit, forming a disk that spirals inward like water circling a drain. As the material moves closer to the center, friction and gravity heat it to incredible temperatures, millions of degrees, causing it to emit light across the electromagnetic spectrum, from radio waves to X-rays. This glowing disk is what we call an accretion disk, and it's one of the most efficient energy-producing machines in the universe. In fact, the light from these disks can outshine entire galaxies, making them some of the brightest objects we can observe. Quasars are a prime example of the incredible power of accretion disks. These distant beacons, found at the centers of galaxies, are powered by supermassive black holes feeding on vast amounts of matter. As the material spirals into the black hole, it releases an enormous amount of energy, lighting up the surrounding space with a brilliance that can be seen billions of light years away. Quasars are so bright that they often outshine every star in their host galaxy combined, making them some of the most luminous objects in the universe. And all of this light comes from the glow of matter being pulled apart and heated to extreme temperatures by gravity's unyielding grip. But accretion disks aren't just cosmic light shows, they're also key to understanding how black holes and neutron stars interact with their surroundings. The intense radiation from these disks can push gas and dust away, influencing the formation of stars and shaping the evolution of entire galaxies. In some cases, the energy from an accretion disk can even launch jets of particles at nearly the speed of light, creating structures that stretch across thousands of light years. These jets, powered by the magnetic fields and intense heat of the disk, are a testament to the dynamic and interconnected nature of the universe. At the heart of every accretion disk lies a deeper mystery, the nature of spacetime itself. As matter spirals closer to a black hole, the effects of gravity become so extreme that they warp time and space in ways that defy our everyday understanding. Time slows down, light bends, and the very fabric of reality is stretched to its limits. This interplay between gravity, light, and spacetime is what makes accretion disks not just fascinating to observe, but also crucial to our understanding of the universe's most fundamental laws. The next time you look up at the night sky, remember that some of the brightest lights in the cosmos come from the glow of matter falling into the abyss. These accretion disks are more than just beautiful, they're windows into the extreme physics that govern the universe, revealing the delicate balance between creation and destruction, light and darkness, order and chaos. And as we continue to study these cosmic engines, we're reminded that even in the most extreme corners of the universe, there's a story waiting to be told, a story of gravity, light, and the dance of matter itself. Einstein's theory of general relativity introduced a revolutionary idea: space-time. Think of it as a four-dimensional fabric woven together from the three dimensions of space and the one dimension of time. This fabric isn't rigid, it's flexible, bending and stretching in response to the presence of massive objects. To visualize this, picture a stretched rubber sheet. Place a bowling ball in the center, and the sheet dips, creating a curve. Now, imagine that bowling ball as a star or a planet, and the rubber sheet as the fabric of space-time. The heavier the object, the deeper the curve it creates. This curvature is what we experience as gravity. It's not a force pulling objects together in the traditional sense. It's the result of objects moving along the contours of warped space-time. Light, too, is influenced by this bending. When light travels through the cosmos, it doesn't move in a straight line. It follows the curves of space-time. This is why light from distant stars bends as it passes near massive objects like galaxies or black holes, a phenomenon known as gravitational lensing. It's as if the universe has its own set of cosmic highways, with gravity dictating the routes. These warped paths aren't just theoretical. They've been observed and measured, confirming Einstein's predictions. The bending of light around massive objects isn't just a curiosity. It's a testament to the profound connection between gravity and the structure of space-time itself. But space-time isn't just about space, it's also about time. One of the most mind-bending consequences of general relativity is that gravity doesn't just warp space, it warps time as well. Imagine a clock placed near a massive object, like a black hole. To a distant observer, that clock would appear to tick more slowly than one far away from the massive object. This effect, known as time dilation, shows that time itself isn't constant. It's relative, shaped by the gravitational forces around it. The closer you are to a massive object, the slower time moves for you compared to someone in a weaker gravitational field. It's a strange and counterintuitive idea, but it's been confirmed by experiments with atomic clocks on Earth and observations of distant cosmic phenomena. What does this mean for our understanding of reality? Space-time isn't just a backdrop for the universe's events. It's an active participant, shaped by the matter and energy within it. Every star, every planet, every speck of dust contributes to the curvature of space-time, influencing the paths of light and the flow of time. This interconnectedness reveals a universe that's far more dynamic and interwoven than we once imagined. It's not just a collection of objects floating in space. It's a living, breathing fabric, constantly shifting and reshaping itself in response to the forces within it. As we explore the implications of space-time, we're reminded that the universe operates on a scale far beyond our everyday experience. Yet, these ideas aren't just abstract concepts. They shape the reality we live in, from the ticking of a clock to the light we see from distant stars. The warping of space-time isn't just a scientific curiosity. It's a fundamental part of the cosmos, a reminder that the universe is far stranger and far more beautiful than we ever imagined. And as we continue to unravel its mysteries, we're learning to see the universe not just as a place of objects, but as a tapestry woven from the threads of space and time. Imagine a clock ticking slower the closer it gets to a massive object like a black hole. This isn't science fiction. It's a real phenomenon called time dilation, one of the most fascinating consequences of gravity's grip on the universe. According to Einstein's theory of general relativity, gravity doesn't just bend space, it warps time itself. The stronger the gravitational field, the slower time moves relative to areas with weaker gravity. It's a concept that challenges our everyday experience, where time feels constant and unchanging, but in the cosmos, time is far more fluid, shaped by the immense forces at play. This effect isn't just theoretical, it has real-world applications, like the Global Positioning System, or GPS, which we rely on every day. GPS satellites orbit Earth at high altitudes, where gravity is slightly weaker than on the surface. Because of this, time on these satellites ticks faster than it does on the ground by about 38 microseconds each day. If engineers didn't account for this difference, GPS calculations would be off by several kilometers, making the system useless for navigation. It's a remarkable example of how even a tiny distortion in time, caused by gravity, has a tangible impact on our lives. But the effects of time dilation become truly mind-bending near the most extreme objects in the universe, black holes. Picture an astronaut falling toward a black hole's event horizon, the point of no return. To an outside observer, the astronaut's clock would appear to slow down dramatically, almost as if time were freezing. Near the black hole's immense gravity, seconds stretch into hours, minutes into years. For the astronaut, time would feel normal, but to anyone watching from afar, their descent would seem to take an eternity. This extreme stretching of time is one of the most dramatic demonstrations of gravity's power, and a reminder of how much the universe can defy our expectations. So how do we measure these distortions in time? Light plays a crucial role. By observing how light behaves near massive objects, scientists can infer the effects of gravity on time. For example, the light emitted from the surface of a neutron star, a super-dense remnant of a collapsed star, is redshifted, meaning its wavelength stretches as it escapes the star's intense gravity. This redshift is a direct consequence of time dilation, providing a way for astronomers to measure the slowing of time in extreme environments. Even the faint glow of an accretion disk around a black hole carries subtle clues about how gravity warps time and space. Time dilation isn't just a curious quirk of the universe. It's a fundamental part of how gravity shapes reality. From the precise calculations of GPS satellites to the mind-bending distortions near black holes, this phenomenon reveals the deep connection between gravity, time, and light. It's a reminder that the universe operates on rules far stranger and more beautiful than we can see with the naked eye. And as we continue to explore these effects, we're uncovering not just the secrets of the cosmos, but the very nature of time itself. The universe is full of whispers, and some of the most profound come in the form of gravitational waves, ripples in the very fabric of spacetime itself. These waves aren't caused by gentle disturbances. They're born from the most violent events in the cosmos, like the collision of black holes or the explosive merging of neutron stars. Picture two black holes spiraling toward each other, their immense gravity distorting spacetime like a stone dropped into a pond. When they finally collide, the impact sends shockwaves rippling outward at the speed of light, stretching and compressing spacetime as they travel across the universe. These ripples are gravitational waves, and they carry with them the echoes of some of the most dramatic events in existence. But how do we detect something as subtle as a ripple in spacetime? The answer lies in some of the most sensitive instruments ever built, detectors like LIGO and Virgo. These massive observatories, spanning kilometers in length, use laser beams to measure tiny changes in the distance between mirrors. When a gravitational wave passes through Earth, it distorts spacetime, causing the mirrors to move ever so slightly. The shift is incredibly small, thousands of times smaller than the width of a proton. But LIGO and Virgo are designed to pick up these minuscule changes. It's like listening to the faintest whisper in a crowded room, and it's opened up an entirely new way to observe the universe. This partnership between light and gravity is what makes gravitational wave detection so groundbreaking. While traditional telescopes rely on light to reveal the cosmos, gravitational wave observatories allow us to listen to the universe in a completely different way. When two black holes merge, for example, they don't emit light, but they do send out gravitational waves. By combining observations from both light and gravitational waves, we can piece together a fuller picture of these cataclysmic events. It's like having both sight and sound to understand a story, each complementing the other to reveal details we might otherwise miss. One of the most remarkable examples of this synergy came in 2017, when LIGO and Virgo detected gravitational waves from the merger of two neutron stars. Almost simultaneously, telescopes around the world observed a burst of light from the same event, marking the first time an astronomical phenomenon had been detected in both gravitational waves and light. This historic discovery provided unprecedented insights into the nature of neutron stars, the origins of heavy elements like gold and platinum, and even the rate at which the universe is expanding. It was a triumph of collaboration between gravity and light, showing how these two forces work together to deepen our understanding of the cosmos. Gravitational waves don't just reveal the secrets of black holes and neutron stars, they also offer clues about the universe's expansion. As these ripples travel across the cosmos, they carry information about the distances between objects and the rate at which the universe is stretching. By studying gravitational waves, scientists can test theories about dark energy, the mysterious force driving the universe's accelerated expansion. It's a new frontier in astronomy, one that promises to shed light on some of the biggest questions in physics. The detection of gravitational waves is more than just a scientific achievement. It's a reminder of how interconnected the universe truly is. From the collision of black holes to the stretching of spacetime itself, these ripples reveal the hidden symphony of the cosmos. And as we continue to listen, we're uncovering not just the secrets of the universe, but the ways in which gravity and light work together to shape the reality we see. The story of gravitational waves is still being written, and each new detection brings us closer to understanding the cosmic dance that defines our existence. As we peer deeper into the cosmos, one of the most profound mysteries we uncover is the universe itself, not as a static stage, but as a dynamic, ever-expanding entity. At the heart of this cosmic drama lies a tug-of-war between two opposing forces: gravity, the great unifier that pulls matter together, and dark energy, the enigmatic force that pushes the universe apart. These two forces are locked in an eternal struggle, shaping the fate of the cosmos in ways we're only beginning to understand. Gravity, as we've seen, is the sculptor of the universe, the force that binds stars into galaxies and galaxies into clusters. It's what keeps planets in their orbits and holds the cosmic web together. But in the late 1990s, astronomers made a startling discovery. The universe isn't just expanding, it's accelerating. This revelation came from observations of distant supernovae, the explosive deaths of massive stars. By measuring how quickly these supernovae were moving away from us, scientists expected to find that the expansion of the universe was slowing down, pulled by gravity's relentless grip. Instead, they found the opposite: the expansion was speeding up, as if some invisible force were pushing galaxies apart faster and faster. This mysterious force is what we now call dark energy. Unlike gravity, which pulls matter together, dark energy acts as a kind of cosmic repulsion, stretching the fabric of spacetime itself. It's as if the universe has an invisible engine, steadily driving galaxies away from each other. Today, dark energy makes up about 68% of the universe's total energy, dwarfing even dark matter. But what exactly is dark energy? That's one of the biggest questions in modern science. Some theories suggest it's a property of space itself, a kind of energy inherent to the vacuum of the cosmos. Others propose it's a new kind of force, one we've yet to fully understand. Whatever it is, its effects are undeniable, reshaping the universe on the grandest scales. The story of this cosmic tug of war isn't just about distant galaxies, it's about the ultimate fate of the universe. If gravity were the dominant force, the universe might eventually stop expanding and begin to collapse, leading to a big crunch where everything is pulled back into a single point. But with dark energy in the picture, the future looks very different. If dark energy continues to dominate, the universe's expansion will keep accelerating. Over billions of years, galaxies will drift further and further apart, their light stretched into invisibility. Stars will burn out, and the cosmos will grow cold and dark, a scenario astronomers call the Big Freeze. It's a stark and sobering vision, but also a reminder of how dynamic and ever-changing the universe truly is. Yet, even as dark energy pushes the universe apart, gravity continues to shape the structures within it. Galaxies collide, stars form, and planets orbit their suns, all governed by the same force that has shaped the cosmos since its birth. This interplay between gravity and dark energy is a reminder that the universe is a place of both creation and destruction, of forces that build and forces that unravel. It's a delicate balance, one that defines the very nature of reality. As we continue to explore the cosmos, we're not just uncovering the secrets of dark energy, we're learning about the universe's past, present, and future. Every distant galaxy, every supernova, every flicker of light carries clues about this cosmic struggle, and with each new discovery, we're reminded that the universe is far more complex and far more wondrous than we ever imagined. The dance between gravity and dark energy is far from over, and as we watch it unfold, we're not just observers, we're participants in the story of the cosmos. What does the future hold for the universe? Will it expand forever, growing colder and darker, or will gravity eventually pull everything back together in a fiery collapse? These two possibilities, heat death and the Big Crunch, represent the leading theories about how the cosmos might end. Each scenario paints a vastly different picture of the universe's ultimate fate, and both are shaped by the interplay of gravity, light, and dark energy. As we explore these cosmic destinies, we're reminded not just of the universe's grandeur, but also of our own fleeting place within it. Let's start with heat death, the scenario that emerges if dark energy continues to dominate. In this vision of the future, the universe's expansion accelerates, pushing galaxies further and further apart. Over trillions of years, stars will burn through their fuel, galaxies will fade, and the cosmos will grow colder and darker. Eventually, even black holes will evaporate, leaving behind a vast, empty expanse of space. This is the heat death of the universe, a state where all energy is evenly distributed and no work or change is possible. It's a quiet, almost poetic end, a universe that simply runs out of steam, its light fading into nothingness. But what role do gravity and light play in this scenario? Gravity, once the great unifier, becomes overwhelmed by dark energy's relentless push, losing its grip on the cosmic web. Light, too, loses its purpose, as there are no stars left to shine and no eyes left to see. Now, contrast this with the Big Crunch, a dramatic reversal of the universe's expansion. In this scenario, gravity eventually overcomes dark energy, pulling galaxies back together in a cosmic collapse. Imagine a universe where every star, every planet, and every particle is drawn toward a single point, compressing into an infinitely dense state. This is the Big Crunch, a fiery end that mirrors the Big Bang in reverse. Here, gravity takes center stage, its pull growing stronger as the universe contracts. Light, once a beacon of creation, would be swallowed by the growing density of matter, its wavelengths stretched and compressed as space-time itself collapses. It's a cosmic finale marked by intensity and destruction, a stark contrast to the slow fade of heat death. But how do we decide which of these fates is more likely? The answer lies in the delicate balance between gravity and dark energy. Right now, dark energy seems to have the upper hand, driving the universe's accelerated expansion. But if that balance shifts, if gravity grows stronger or dark energy weakens, the scales could tip toward a big crunch. It's a reminder that the universe is a dynamic, ever-changing place, shaped by forces we're still striving to understand. As we ponder these cosmic futures, it's hard not to reflect on humanity's place in this vast expanse. Our existence is a fleeting moment in the universe's timeline, a blink of an eye compared to the eons that have passed and the eons yet to come. Yet, in that brief moment, we've managed to uncover some of the universe's deepest secrets, from the nature of gravity and light to the mysteries of dark energy and dark matter. We've built telescopes to peer into the distant past and detectors to listen to the ripples of spacetime itself. In doing so, we've become witnesses to the cosmic dance, participants in a story that stretches far beyond our own lives. The universe's fate may be uncertain, but our quest to understand it is a testament to the power of curiosity and discovery. Whether the cosmos ends in a slow fade or a fiery collapse, one thing is clear: the dance of gravity, light, and dark energy will continue to shape its story until the very end. And as we watch that story unfold, we're reminded of our own small but significant role in the grand tapestry of existence. The universe is vast, but it's also ours to explore, to understand, and to marvel at, one discovery at a time. As we stand on the edge of the cosmos, gazing into the vast expanse of stars and galaxies, we're reminded of our unique role in the universe. We are its observers, its storytellers, and its seekers of truth. Through the interplay of gravity and light, we've unlocked the secrets of the cosmos, from the birth of stars to the collision of black holes. But this journey isn't just about science, it's about what it means to be human in a universe so vast and mysterious. Our ability to perceive and study these forces is a gift, one that allows us to connect with the cosmos in ways that are both profound and humbling. Think about it for a moment. Every time we look at the night sky, we're not just seeing points of light, we're witnessing the echoes of events that happened millions, even billions, of years ago. Light traveling across unimaginable distances carries the stories of stars long gone, of galaxies colliding, and of black holes devouring matter. Gravity, the silent architect, shapes these stories, bending light and warping spacetime to create the cosmic tapestry we see. And through our telescopes, our detectors, and our curiosity, we've learned to read this tapestry, to decode the universe's secrets and understand our place within it. But our role as observers goes beyond mere observation. It's about interpretation, about finding meaning in the patterns of light and the distortions of spacetime. When we detect gravitational waves rippling through the cosmos, we're not just hearing the echoes of colliding black holes, we're listening to the universe's heartbeat. When we observe the bending of light around a massive galaxy, we're not just seeing a cosmic illusion, we're glimpsing the hidden architecture of reality. These moments remind us that the universe is not just a place of objects and forces, it's a place of stories waiting to be told. Yet, as much as we've learned, there's still so much we don't know. The universe is vast, and its mysteries are deep. What lies beyond the event horizon of a black hole? What is the true nature of dark matter and dark energy? How did the universe begin, and what will its ultimate fate be? These questions drive us forward, pushing the boundaries of our knowledge and inspiring the next generation of explorers. And as we continue to explore, we're not just uncovering the secrets of the cosmos, we're uncovering the secrets of ourselves. Looking to the future, the tools we use to study the universe are evolving at an astonishing pace. Telescopes like the James Webb Space Telescope and observatories like LIGO and Virgo are just the beginning. In the coming decades, new technologies will allow us to see further, hear more, and probe deeper into the universe's mysteries. Imagine telescopes that can map the entire cosmic web in unprecedented detail, or detectors so sensitive they can pick up the faintest whispers of gravitational waves from the earliest moments of the Big Bang. These advancements won't just deepen our understanding, they'll transform it, revealing new layers of the cosmic dance that we can't yet imagine. But perhaps the most profound implication of our role as observers is the way it connects us to the universe. In studying gravity and light, we're not just exploring distant galaxies or abstract forces, we're exploring the very fabric of reality, the threads that weave together the cosmos and everything in it. And in doing so, we're reminded that we are not separate from the universe, but a part of it, shaped by the same forces and bound by the same laws. The light we see, the gravity we feel, it's all part of the same story, a story that began billions of years ago and continues to unfold with every discovery we make. So, as we look to the future, let's remember that our journey is far from over. The universe is vast, and its mysteries are endless, but so too is our capacity to explore, to learn, and to wonder. With every new discovery, we're not just uncovering the secrets of the cosmos, we're writing the next chapter of humanity's story. A story that is as much about the stars above as it is about the curiosity and courage that drive us to reach for them. The cosmic dance continues, and we, as its observers, are privileged to witness it, to understand it, and to be a part of it. The universe is a treasure trove of mysteries, and as we continue to explore, we're developing tools that allow us to dig even deeper into its secrets. Imagine a future where we can listen to the faintest whispers of gravitational waves from the edge of the cosmos or peer into the hearts of galaxies with unprecedented clarity. This isn't science fiction, it's the promise of next-generation technologies like the Laser Interferometer Space Antenna, or LISA, and a new wave of advanced telescopes. These groundbreaking tools are set to revolutionize our understanding of gravity, light, and the very fabric of reality itself. LISA, a mission planned by the European Space Agency, is one of the most ambitious projects on the horizon. Unlike ground-based detectors like LIGO, LISA will operate in space, forming a constellation of 3 satellites separated by millions of kilometers. This vast network will allow LISA to detect gravitational waves at lower frequencies than ever before, opening a window into events like the mergers of supermassive black holes and the earliest moments of the universe's formation. Think of it as a cosmic microphone, tuned to hear the universe's deepest, most resonant note sounds that have been traveling through space for billions of years. With LISA, we'll not only observe these events, but also test the limits of Einstein's theory of general relativity, potentially uncovering hints of new physics or even hidden dimensions. But LISA is just one piece of the puzzle. On the ground and in space, a new generation of telescopes is poised to transform our view of the cosmos. The Extremely Large Telescope, or ELT, currently under construction in Chile, will boast a mirror nearly 40 meters wide, more than 4 times the size of today's largest telescopes. With this incredible resolution, the ELT will allow us to study the atmospheres of distant exoplanets, track the formation of stars in unprecedented detail, and even probe the nature of dark matter and dark energy. Meanwhile, space-based telescopes like the Nancy Grace Roman Space Telescope will map the universe in infrared light, revealing hidden structures and shedding light on the cosmic web that connects galaxies across vast distances. These technologies aren't just about seeing farther, they are about seeing differently. By combining observations from gravitational wave detectors and telescopes, we'll gain a richer, more complete picture of the universe. For example, when LISA detects a gravitational wave signal from colliding black holes, telescopes could simultaneously capture the light from the event, providing a multi-messenger view that reveals details no single instrument could uncover alone. It's like having both ears and eyes to explore the cosmos, each sense enhancing the other to reveal a fuller story. Yet, as powerful as these tools are, they also remind us of the limits of our current knowledge. Despite our incredible advancements, there are still questions that elude us. What happens inside a black hole's event horizon? How do gravity and quantum mechanics fit together? These are the frontiers of modern physics, and they're challenges that next-generation technologies are uniquely equipped to tackle. By probing the behavior of gravity at its most extreme, we might uncover clues about quantum gravity, a theory that unites the macroscopic world of general relativity with the microscopic realm of quantum physics. It's a puzzle that has stumped scientists for decades, but with tools like LISA and the ELT, we're closer than ever to finding answers. The future of astronomy and physics is filled with promise, but it's also a reminder of how much we have yet to discover. Every new tool we build, every mission we launch, brings us closer to understanding the cosmic dance of gravity and light. And as we push the boundaries of our knowledge, we're not just exploring the universe. We're redefining what it means to be curious, to be human, and to seek answers to the biggest questions of all. The dance continues, and with each step forward, we're learning to move in rhythm with the cosmos. For all the progress we've made in understanding the universe, there are still profound mysteries that elude us, questions that challenge the very limits of human knowledge. Take dark matter, for example. We know it exists because of its gravitational effects on galaxies and galaxy clusters, but we still don't know what it's made of. Is it a yet undiscovered particle, a new kind of force, or something entirely beyond our current understanding? Despite decades of searching, dark matter remains invisible, its true nature one of the greatest puzzles in modern science. And it's not alone. Dark energy, the force driving the universe's accelerated expansion, is equally enigmatic. Together, these two dark components make up about 95% of the universe's total energy and matter. Yet we can't see them, touch them, or even fully explain them. It's a humbling reminder that, for all our advancements, the cosmos still holds secrets beyond our grasp. Then there's the challenge of unifying gravity with quantum mechanics, two of the most successful theories in physics. Quantum mechanics explains the behavior of the smallest particles with astonishing precision, while general relativity describes the vast, cosmic dance of gravity and spacetime. But when it comes to the extremes, like the singularities inside black holes or the conditions of the Big Bang, these theories clash, leaving us with a paradox. How can the same universe be governed by two sets of rules that seem fundamentally incompatible? This question has driven physicists for decades, inspiring theories like string theory and loop quantum gravity, but a definitive answer remains out of reach. It's a puzzle that not only challenges our understanding of the universe, but also pushes the boundaries of human ingenuity. Even space-time itself, the very stage on which the cosmic drama unfolds, is shrouded in mystery. We know it bends and warps under the influence of gravity, but what is it really? Is it a fabric, as Einstein described, or something more abstract? Could it have a structure at the smallest scales, perhaps woven from quantum threads we've yet to discover? These questions aren't just academic, they are fundamental to our understanding of reality. And while we've made incredible strides, from detecting gravitational waves to mapping the cosmic microwave background, we're still far from a complete picture. These mysteries aren't just scientific challenges, they're also philosophical ones. They force us to confront the limits of human knowledge and the nature of discovery itself. What does it mean to explore a universe that's so vast and complex? How do we grapple with the idea that some questions might never have answers? These are questions that go beyond physics, touching on what it means to be curious, to seek, and to wonder. In a way, the unknown is what drives us forward, fueling our desire to explore, to experiment, and to imagine. And that's the beauty of science. It's not just about finding answers. It's about asking better questions. Every discovery opens new doors, revealing deeper layers of the universe's complexity. Whether it's the search for dark matter, the quest to unify gravity and quantum mechanics, or the exploration of spacetime's true nature, these mysteries remind us that the universe is far stranger and more wondrous than we can imagine. They invite us to keep looking, keep questioning, and keep marveling at the cosmic dance that surrounds us. After all, the journey of discovery is just as important as the destination, and in a universe full of mysteries, the journey never truly ends. Consider this: what if the reality we experience is not as concrete as it seems, but more like a cosmic illusion, sculpted by the invisible hand of gravity and the luminous brushstrokes of light? The universe, as we perceive it, is a tapestry woven from these two forces, each thread bending and shaping the fabric of existence. Gravity warps spacetime, creating curves and folds that guide the motion of planets, stars, and even light itself. Light, in turn, carries the images of these warped paths to our eyes, painting a picture that feels real and tangible. But what if this picture is just one interpretation of a far more complex reality? What if the universe is not a static stage, but a dynamic, ever-shifting canvas, one that challenges our very notions of existence and perception? This idea isn't just science, it's philosophy. It forces us to question the nature of reality itself. For centuries, we've assumed that what we see is what exists, that the world around us is as solid and unchanging as it appears. But the interplay of gravity and light tells a different story. When light bends around a massive galaxy, it doesn't just create a beautiful cosmic mirage, it reveals the malleability of spacetime, the fluidity of the universe's structure. This bending isn't an exception, it's the rule. Every photon of light that reaches us has traveled through a labyrinth of gravitational fields, each one altering its path in subtle but profound ways. The reality we perceive, then, is not a direct reflection of the cosmos, but a filtered version, shaped by the forces that govern it. These revelations don't just challenge our understanding of the universe, they challenge our understanding of ourselves. If reality is shaped by forces we can't see or touch, How much of what we experience is truly real? Are we, too, part of this cosmic illusion? Are perceptions shaped by the same forces that bend light and warp spacetime? These questions blur the line between science and philosophy, inviting us to see the universe not just as a place of physical laws, but as a realm of endless wonder and mystery. It's a reminder that the cosmos is not just out there, it's within us, shaping the way we see, think, and exist. But this interplay between gravity, light, and perception isn't just a scientific or philosophical concept, it's also deeply artistic. Think of the way light bends and refracts through a prism, creating a spectrum of colors that dance across a surface, or the way a painter uses shadows and perspective to create depth on a flat canvas. These artistic techniques are not so different from the cosmic dance of gravity and light. In both cases, perception is shaped by the interaction of forces, whether physical or creative. The universe, in this sense, is the ultimate artist, using gravity and light to craft a masterpiece that stretches across billions of light years. Science and art, then, are not so far apart. Both seek to understand and interpret the world around us, to find meaning in the patterns and rhythms of existence. And in the interplay of gravity and light, we find a common ground, a place where the analytical mind of the scientist meets the imaginative soul of the artist. It's a reminder that the universe is not just a machine of physical laws, but a living, breathing work of art, one that invites us to explore, to question, and to marvel. As we navigate this cosmic dance, we're reminded that reality is not a fixed point but a spectrum, shaped by the forces that surround us and the perceptions that define us. The universe is not just a place to study, it's a story to be told, a canvas to be painted, a mystery to be unraveled, and in that unraveling, we find not just answers but new questions, new wonders, and new ways of seeing the world. The dance of gravity and light is not just a scientific phenomenon, it's a journey into the heart of existence itself, one that challenges us to see the universe and ourselves in a whole new light. The interplay of gravity and light isn't just a scientific phenomenon, it's a source of endless inspiration, bridging the worlds of art and science in ways that illuminate both. Think of the iconic image of a black hole, captured for the first time in 2019. This wasn't just a triumph of technology, it was a masterpiece of collaboration. Scientists and artists worked hand in hand to translate raw data into a visual representation, crafting an image that captured the imagination of millions. The glowing ring of light surrounding the black hole's shadow wasn't just a scientific breakthrough, it was a work of art, a testament to the beauty hidden within the cosmos. Art and science have always been intertwined, each offering a unique lens through which to understand the universe. When scientists study the bending of light around massive galaxies, they rely on visualizations to interpret the data. These visualizations, often created by artists, transform abstract concepts into something tangible and relatable. For example, the intricate patterns of gravitational lensing, where light from distant galaxies is bent into arcs and rings, can be difficult to grasp without a visual aid. But through the power of art, these phenomena become accessible, allowing us to see the universe in ways that words alone cannot convey. One of the most striking examples of this collaboration is the visualization of spacetime itself. Scientists describe spacetime as a flexible fabric, warped by the presence of massive objects. But how do you visualize something so abstract? Artists step in, creating animations and illustrations that bring this concept to life. Picture a trampoline with a bowling ball in the center, the surface bending and stretching under its weight. Now imagine that trampoline as the fabric of the universe, with stars and planets creating ripples and curves. These visual metaphors don't just explain the science, they evoke a sense of wonder, helping us connect with the universe on a deeper level. The role of art in science goes beyond visualization. It's also about communication. Complex ideas like the curvature of spacetime or the behavior of light near a black hole can be daunting to grasp, but through art, these ideas become more approachable. Take, for instance, the way artists depict the accretion disks around black holes, glowing rings of superheated gas spiraling inward. These images not only convey the physics at play, but also highlight the sheer beauty of these cosmic phenomena. They remind us that science isn't just about equations and data. It's about exploring the awe-inspiring wonders of the cosmos. But perhaps the most profound connection between art and science lies in their shared pursuit of truth. Artists and scientists both seek to uncover the underlying patterns and rhythms of the universe, whether through brushstrokes or mathematical equations. The swirling arms of a galaxy, the delicate rings of a gravitational lens, the fiery glow of a supernova, these are not just scientific subjects, they are artistic muses, inspiring creativity and curiosity in equal measure. In this way, art and science are two sides of the same coin, each enriching our understanding of the other. As we reflect on the beauty of the universe, it's clear that the cosmic dance of gravity and light is more than just a scientific narrative. It's a story of collaboration and inspiration. Through the combined efforts of artists and scientists, we're able to see the universe in all its complexity and splendor. These visualizations don't just inform us, they move us, reminding us of the profound connection between the cosmos and our own creativity. The universe is not just a place of discovery, it's a canvas waiting to be explored, interpreted, and celebrated. And in that exploration, we find not just answers, but a deeper appreciation for the beauty that surrounds us. The cosmos is not just a realm of scientific discovery, it's a gallery of breathtaking artistry, where gravity and light collaborate to create masterpieces on a scale that defies imagination. Picture the swirling arms of a spiral galaxy, each one a river of stars, gas, and dust, gracefully curving through the void. These elegant structures are sculpted by gravity, the invisible hand that pulls matter into vast, rotating disks. But it's light that brings them to life, illuminating their intricate details and revealing their splendor to us. From the fiery glow of star-forming regions to the delicate wisps of interstellar dust, every galaxy is a testament to the harmonious dance of these two forces. Now, shift your gaze to a nebula, a cosmic cloud where stars are born. These shimmering tapestries of gas and dust are illuminated by the light of newborn stars, their colors ranging from deep reds to brilliant blues. Gravity gathers the material, compressing it into dense clumps that ignite into stellar fire, while light scatters through the clouds, painting the scene with ethereal beauty. The Orion Nebula, for example, is one of the most famous, its vibrant hues and intricate filaments a reminder of the universe's creative power. It's as if the cosmos itself is an artist, using gravity as its chisel and light as its palette. But the beauty of the cosmos isn't just in its grand structures, it's also in the subtle details. Consider the delicate rings of Saturn or the intricate patterns of a solar eclipse. These phenomena, too, are shaped by the interplay of gravity and light. Saturn's rings, for instance, are held in place by the planet's gravitational pull, while sunlight reflects off their icy particles, creating a dazzling spectacle. A solar eclipse, on the other hand, is a cosmic alignment where the moon's gravity blocks the sun's light, casting a shadow that reveals the sun's outer atmosphere, or corona, in stunning detail. These moments remind us that even the smallest cosmic events can inspire awe. This aesthetic beauty is more than just a visual treat. It's a driving force behind humanity's quest to explore the universe. When we see the vibrant colors of a nebula or the graceful arcs of a galaxy, we're not just observing the cosmos, we're connecting with it on a profound level. These images spark curiosity, inspiring us to ask questions, seek answers, and push the boundaries of our knowledge. The Hubble Space Telescope, for example, has not only expanded our scientific understanding, but also brought the beauty of the universe into our homes, captivating millions with its stunning images. It's a reminder that science and wonder are deeply intertwined. As we marvel at these celestial wonders, we're reminded of our place in the universe. The same forces that shape galaxies and nebulae also shape us, connecting us to the cosmos in ways that are both humbling and empowering. The beauty we see in the stars is a reflection of the beauty within us, a shared spark of curiosity and creativity that drives us to explore, to dream, and to discover. And as we continue to uncover the secrets of the universe, we're not just learning about the cosmos, we're learning about ourselves and the infinite potential that lies within our reach. The mysteries of gravity and light are more than just scientific puzzles. They are the sparks that ignite humanity's drive to explore. From the earliest stargazers to the modern day, astronomers peering through colossal telescopes, our fascination with the cosmos has been fueled by a relentless curiosity. What is out there? How does it all work? These questions have propelled us to build instruments, launch missions, and push the boundaries of what we know. But this quest isn't just about satisfying scientific curiosity. It's about understanding our place in the vast tapestry of the universe. Every discovery, from the bending of starlight to the ripples of gravitational waves, brings us closer to answering these profound questions. Curiosity is at the heart of this journey. It's what led Isaac Newton to ponder why an apple falls to the ground, and what inspired Albert Einstein to imagine the warping of spacetime. Today, that same curiosity drives scientists to probe the edges of black holes, map the cosmic web, and search for the invisible threads of dark matter and dark energy. But this curiosity isn't confined to scientists alone. It's a universal trait, shared by anyone who has ever looked up at the night sky and felt a sense of wonder. It's what compels us to ask questions, to seek answers, and to dream of what lies beyond the horizon. Yet, the pursuit of knowledge isn't just about grand cosmic mysteries. It's also deeply personal. Understanding the forces that shape the universe helps us make sense of our own existence. When we learn how gravity binds galaxies together, or how light carries the stories of distant stars, we gain a deeper appreciation for the interconnectedness of all things. This knowledge doesn't just expand our minds, it enriches our lives, offering a sense of perspective and humility. It reminds us that we are part of something much larger than ourselves, a universe that is both awe-inspiring and humbling. The impact of this exploration extends far beyond the realm of science. The technologies developed to study gravity and light, from GPS satellites to medical imaging devices, have transformed our daily lives. The principles of general relativity, once confined to theoretical physics, now enable us to navigate the globe with pinpoint accuracy. Similarly, the study of light has given us tools like lasers and fiber optics, revolutionizing communication and medicine. These innovations are a testament to the power of curiosity-driven research, showing how the pursuit of knowledge can lead to tangible benefits for humanity. But perhaps the most profound impact of this exploration is the way it shapes our worldview. By uncovering the secrets of gravity and light, we're not just learning about the universe, we're learning about ourselves. Every discovery challenges us to rethink our assumptions, to question our place in the cosmos, and to imagine new possibilities. It's a journey that transcends science, touching on philosophy, art, and the very essence of what it means to be human. And as we continue to explore, we're reminded that the universe is not just a place to study, it's a source of endless inspiration, a canvas for our curiosity, and a mirror reflecting our deepest questions. So, the next time you gaze at the stars, remember that you're part of a story that spans billions of years. The same forces that shape the cosmos also shape us, connecting us to the universe in ways that are both profound and beautiful. And as we continue to explore, we're not just uncovering the secrets of gravity and light, we're uncovering the secrets of ourselves, one discovery at a time. The dance of gravity and light isn't confined to the far reaches of the cosmos. It's woven into the fabric of our everyday lives. Take GPS, for example, a technology many of us rely on daily. Without Einstein's theory of general relativity, your smartphone's navigation system wouldn't work. GPS satellites orbit Earth at high altitudes, where gravity is slightly weaker than on the ground. This difference means time ticks faster for the satellites by about 38 microseconds each day. If engineers didn't account for this relativistic effect, GPS calculations would be off by several kilometers, leading you astray instead of guiding you home. It's a striking example of how our understanding of gravity's influence on time has transformed a once theoretical concept into a practical tool that millions use without a second thought. But the impact of gravity and light doesn't stop there. In the field of medical imaging, light, or more specifically, electromagnetic waves, plays a starring role. Technologies like MRI or magnetic resonance imaging rely on the behavior of light and its interaction with matter to create detailed images of the human body. By using powerful magnets and radio waves, MRI machines can detect the subtle differences in how hydrogen atoms in your body respond to electromagnetic fields. These responses are then translated into high-resolution images, allowing doctors to diagnose conditions with remarkable precision. It's a testament to how the principles of light and electromagnetism, once the domain of abstract physics, have become indispensable in modern medicine. Then there's the role of light in fiber optics, the backbone of global communication. Light pulses travel through thin glass fibers, carrying vast amounts of data across continents in the blink of an eye. This technology, rooted in our understanding of how light behaves, has revolutionized everything from internet connectivity to telemedicine, shrinking the world and bringing people closer together. Without the study of light's properties, its speed, its ability to reflect and refract, none of this would be possible. These innovations remind us that the cosmic dance of gravity and light isn't just a distant spectacle. It's a force that shapes the tools and technologies we depend on every day. Yet, with great knowledge comes great responsibility. As we harness the power of gravity and light to improve our lives, we must also consider the ethical implications of this progress. For instance, the precision of GPS has revolutionized navigation, but it also raises questions about privacy and surveillance. Who has access to location data, and how is it being used? Similarly, medical imaging technologies like MRI have transformed healthcare, but they also come with challenges, such as ensuring equitable access to these advanced tools. The benefits of scientific discovery are immense, but they must be balanced with thoughtful consideration of their impact on society. These ethical questions remind us that the pursuit of knowledge is not just about discovery, it's about responsibility. As we continue to explore the mysteries of gravity and light, we must also reflect on how to use this knowledge wisely. The same forces that guide stars and bend light also guide our decisions, shaping the future of technology, society, and our place within the cosmos. It's a reminder that science is not just a journey of exploration, but also a call to action, urging us to use our understanding for the greater good. As we unlock the secrets of gravity and light, we step into a realm of immense power, and with it, profound responsibility. The knowledge we gain isn't just a tool for understanding the cosmos, it's a force that can shape the future of humanity. But as we harness these fundamental forces, we must ask ourselves, how do we use this power wisely? The ethical considerations that come with understanding gravity and light are as vast as the universe itself, touching on everything from technological innovation to the very fabric of our society. Take, for example, the manipulation of light. Technologies like lasers and fiber optics have revolutionized communication, medicine, and even entertainment. But these advancements also raise ethical questions. Who controls access to these tools? How do we ensure they're used equitably and responsibly? The same light that allows us to perform life-saving surgeries can also be weaponized, highlighting the dual nature of scientific progress. It's a reminder that knowledge, no matter how groundbreaking, must be guided by a moral compass. Gravity, too, presents its own set of challenges. While we've yet to master this force on a large scale, theoretical concepts like artificial gravity or gravitational wave manipulation open doors to incredible possibilities and potential risks. Imagine a future where we could control gravity itself, bending it to our will. Such power could transform space travel, energy production, and even our understanding of physics. But it also raises questions about the consequences. What happens if this technology falls into the wrong hands? How do we balance innovation with the need to protect our planet and its inhabitants? These ethical dilemmas aren't just hypothetical. They're deeply interconnected with the way we live and interact with the world. Every breakthrough in understanding gravity or light has ripple effects, influencing everything from global economies to individual lives. The decisions we make today about how to use this knowledge will shape the future for generations to come. It's a responsibility that transcends science, touching on philosophy, ethics, and the very essence of what it means to be human. At the heart of these considerations is a simple truth: we are all connected. The forces that shape the cosmos also shape us, binding us to each other and to the universe itself. This interconnectedness is both a challenge and an opportunity. It reminds us that our actions, no matter how small, have consequences that extend far beyond ourselves. Whether it's developing new technologies or making ethical decisions about their use, we are part of a larger story, one that demands thoughtfulness, compassion, and a commitment to the greater good. In the end, the exploration of gravity and light is more than a scientific endeavor. It's a journey of discovery that challenges us to grow, not just as thinkers, but as stewards of the universe. As we continue to uncover the secrets of these fundamental forces, let's also strive to cultivate the wisdom needed to use them responsibly. The cosmos may be vast and mysterious, but it's also a mirror reflecting back the best, and sometimes the most challenging aspects of who we are. And in that reflection, we find not just answers, but the opportunity to create a future that honors the beauty and complexity of the universe we call home. At the heart of the cosmos lies a profound truth: everything is connected. Gravity and light, the two fundamental forces we've explored, aren't just isolated phenomena. They are threads in a vast cosmic tapestry, weaving together everything from the tiniest particles to the grandest galaxies. Picture the universe as a web, with each strand representing the influence of gravity or the flow of light. A star's gravity shapes the orbit of its planets, while its light travels billions of years to reach our eyes. A distant galaxy bends the path of light from an even more distant quasar, creating a cosmic lens that reveals the hidden structure of spacetime. These forces don't just exist in isolation, they interact, overlap, and intertwine, creating the intricate patterns that define reality. This interconnectedness isn't just a poetic notion, it's a scientific reality. Gravity, for instance, doesn't operate in a vacuum. It's a universal force, pulling on every speck of matter, from the dust in your home to the stars in the sky. Light, too, is a universal messenger, carrying information across the cosmos and revealing the hidden connections between distant objects. When we observe the light from a distant galaxy, we're not just seeing a point in space. We're glimpsing a moment in time, a piece of a story that spans billions of years. These connections remind us that the universe is not a collection of isolated objects, but a dynamic, interwoven whole. But what does this mean for our understanding of existence? If gravity and light connect all things, then every action, no matter how small, ripples through the fabric of reality. A star's explosion sends shockwaves through space, influencing the formation of new stars and planets. A black hole's immense gravity bends the light from distant galaxies, altering our perception of the cosmos. Even the light from your screen, as you watch this video, is part of this grand web, a tiny thread in the vast tapestry of the universe. This perspective shifts how we see ourselves, not as separate observers, but as active participants in the cosmic dance. This brings us to a fascinating question. What role does consciousness play in this interconnected web? After all, it's through our awareness that we perceive and interpret the universe. The light from distant stars reaches our eyes, and our brains transform it into images and ideas. Gravity shapes the paths of planets and galaxies, but it's our minds that make sense of these patterns, turning them into laws and theories. In this way, consciousness is not just a passive observer, it's an integral part of the web, shaping and being shaped by the forces that surround us. Consider the act of observing the night sky. When you look at a star, you're not just seeing a point of light, you're engaging in a dialogue with the cosmos. The light from that star has traveled across space and time to reach you, and your perception of it is shaped by the unique interplay of gravity, light, and your own consciousness. It's a reminder that reality is not something fixed and unchanging. It's a dynamic, ever-evolving relationship between the observer and the observed. This idea challenges us to rethink our place in the universe, not as outsiders looking in, but as active participants in the unfolding story of existence. The interconnectedness of gravity, light, and consciousness invites us to see the universe in a new light, not as a cold, distant place, but as a living, breathing entity full of wonder and mystery. It's a perspective that bridges science and philosophy, offering a deeper understanding of our place in the cosmos. As we continue to explore these connections, we're not just uncovering the secrets of the universe, we're discovering the threads that bind us to it and to each other. And in that discovery, we find not just answers, but a deeper sense of connection to the vast, beautiful web of reality. What if the universe we perceive isn't just a collection of stars and galaxies, but a reflection of our own consciousness? The way we interpret gravity and light through our senses, our instruments, and our minds plays a crucial role in shaping the reality we experience. When we look at the night sky, we're not just observing distant objects, we're engaging in a deeply personal act of perception. Our brains take the raw data of light and gravity photons traveling through curved spacetime and weave them into a coherent picture of the cosmos. But this picture isn't a perfect replica of the universe. It's a construction shaped by the limitations and capabilities of our senses and cognition. Think about the way light bends around a massive galaxy, creating the phenomenon of gravitational lensing. To our eyes, this might appear as a distorted arc or a ring of light. But without the tools of science, telescopes, mathematical models, and theoretical frameworks, we wouldn't understand the underlying mechanisms at play. Our perception of this cosmic mirage is filtered through layers of interpretation, from the way our eyes process light to the way our brains make sense of complex patterns. In other words, the universe doesn't just exist out there, it's also a product of how we perceive and interpret it. This raises an intriguing question: how much of reality is shaped by the observer? Quantum physics has long grappled with the idea that the act of observation can influence the behavior of particles. While gravity and light operate on much larger scales, the principle still holds. Our understanding of the cosmos is deeply intertwined with the tools and frameworks we use to study it. Even the most advanced telescopes and detectors rely on human interpretation to make sense of the data they collect. In this sense, the universe is not just a physical entity, it's also a conceptual one, shaped by the questions we ask and the ways we seek answers. But perception isn't just a passive process, it's also creative. When we see the swirling arms of a spiral galaxy or the glowing tendrils of a nebula, our minds don't just register these images, they imbue them with meaning. We connect the dots, seeing patterns and stories in the stars. This creative aspect of perception is what transforms raw data into art, science, and wonder. It's what allows us to see not just what's there, but what could be, to imagine new possibilities and explore the unknown. Yet, for all our advances, there are still mysteries that elude us. Dark matter and dark energy, for example, remain invisible to our senses and our instruments. We infer their existence through their gravitational effects, but we can't directly observe them. These gaps in our understanding remind us that the universe is far more complex than our current models suggest. They challenge us to keep questioning, to keep exploring, and to remain open to the possibility that reality may be stranger than we can imagine. As we reflect on the role of consciousness in shaping our perception of gravity and light, we're reminded that the cosmos is not just a place of physical laws, it's also a realm of ideas, interpretations, and possibilities. Every time we look at the stars, we're not just seeing the universe, we're seeing a reflection of ourselves, our curiosity, and our capacity to wonder. And in that reflection, we find not just answers, but new questions, new mysteries, and new ways of understanding the beautiful, interconnected web of reality. As we've journeyed through the cosmic dance of gravity and light, uncovering their profound partnership, one thing becomes clear: the universe is far from fully understood. Even with all our advancements, some of the most fundamental questions remain unanswered, standing as towering frontiers in the realm of science. These unsolved mysteries aren't just gaps in our knowledge, they're invitations to explore, to question, and to dream. They challenge us to push the boundaries of what we know, driving the relentless pursuit of discovery. One of the most perplexing puzzles lies at the heart of black holes: the singularity. According to Einstein's theory of general relativity, a singularity is a point where gravity becomes infinitely strong, space-time curvature becomes infinite, and the laws of physics as we know them break down. But what does this really mean? Is it a true point of infinite density, or is there something more? A doorway to new physics, perhaps even to other dimensions? The truth is, we don't know. Our current understanding of gravity and spacetime falters at the singularity, leaving us with more questions than answers. This mystery isn't just academic, it's a call to rethink the very foundations of our understanding of the universe. Then there's the tantalizing possibility of faster-than-light travel, a concept that has captivated scientists and science fiction writers alike. According to Einstein's theory, nothing can travel faster than light. But what if there's a way to bend the rules? Wormholes, hypothetical tunnels through spacetime, offer one intriguing possibility. These cosmic shortcuts could, in theory, connect distant parts of the universe, allowing travel that appears faster than light. Yet, wormholes remain purely theoretical, and their existence raises a host of questions. How could they be stabilized? Could they even exist without collapsing under their own gravity? These questions aren't just idle speculation. They're driving scientists to explore the outer limits of what's possible. Another frontier lies in the realm of quantum gravity, the elusive theory that seeks to unify general relativity with quantum mechanics. While general relativity describes gravity as the curvature of spacetime, quantum mechanics governs the behavior of particles on the smallest scales. The problem: these two theories are fundamentally incompatible, leaving us without a complete picture of how gravity operates in the quantum realm. Solving this puzzle could unlock answers to some of the universe's deepest mysteries, from the nature of singularities to the origins of the cosmos itself. It's a challenge that has inspired some of the brightest minds in physics, from string theorists to loop quantum gravity researchers, each offering their own unique perspectives. But these mysteries aren't just scientific challenges, they're opportunities for collaboration. No single scientist, no single field can tackle these questions alone. It takes a collective effort, bringing together physicists, mathematicians, engineers, and even philosophers, each contributing their expertise to the quest for knowledge. Collaboration is the cornerstone of scientific progress, and it's through this shared effort that we've made some of our greatest discoveries. From the detection of gravitational waves to the mapping of the cosmic microwave background, these breakthroughs are the result of countless minds working together toward a common goal. As we stand on the edge of these frontiers, we're reminded that the pursuit of knowledge is a journey, not a destination. The mysteries of gravity and light aren't just obstacles to overcome, they are invitations to explore, to innovate, and to imagine. They remind us that the universe is far more complex, far more wondrous than we can currently comprehend. And as we continue to push the boundaries of our understanding, we're not just uncovering the secrets of the cosmos, we're uncovering the potential within ourselves to dream, to discover, and to shape the future of science. The journey is far from over, and with every step, we're reminded of the boundless possibilities that lie ahead. The mysteries of gravity and light are not confined to a single field of study. They stretch across the boundaries of physics, astronomy, mathematics, and even philosophy. Solving these cosmic puzzles requires more than just individual brilliance. It demands collaboration, a meeting of minds that brings together diverse perspectives and expertise. Think of it as a symphony, where each discipline plays a unique instrument, blending their contributions to create a harmonious understanding of the universe. From the earliest stargazers to the modern day, scientists working in cutting-edge labs, it's this spirit of teamwork that has driven our greatest discoveries. One of the most striking examples of this collaborative effort is the detection of gravitational waves in 2015. This groundbreaking discovery was the result of decades of work by teams of physicists, engineers, and computer scientists from around the world. LIGO, the Laser Interferometer Gravitational Wave Observatory, brought together experts in optics, quantum mechanics, and data analysis to build instruments sensitive enough to detect ripples in spacetime smaller than a proton. But the collaboration didn't stop there. Astronomers followed up with telescopes, searching the skies for the light produced by the neutron star collision that generated the waves. Together, these teams achieved something extraordinary, the first ever observation of a cosmic event in both gravitational waves and light. It was a triumph of interdisciplinary science, proving that the universe's secrets are best unlocked when we work together. Another remarkable example is the study of dark matter and dark energy, two of the most elusive concepts in modern physics. Solving these mysteries requires the combined efforts of cosmologists, particle physicists, and observational astronomers. Cosmologists use models to predict how dark matter and dark energy shape the universe, while particle physicists search for clues in the behavior of subatomic particles. Meanwhile, astronomers map the distribution of galaxies and measure the universe's expansion, gathering data that tests these theories. It's a collaborative dance where each discipline contributes a piece of the puzzle, bringing us closer to understanding the universe's hidden structure. But collaboration in science isn't just about pooling technical expertise, it's also about asking the right questions. This is where philosophy plays a crucial role, guiding scientists to think deeply about the nature of reality, the limits of knowledge, and the ethical implications of their discoveries. For instance, the philosophical debate over the interpretation of quantum mechanics has shaped how physicists approach the study of light and matter. Similarly, questions about the nature of time and space, central to Einstein's theories, continue to inspire both scientists and philosophers to explore the boundaries of human understanding. At the heart of this collaborative spirit is curiosity, the driving force that propels us to explore the unknown. Curiosity is what unites physicists peering into the quantum realm, astronomers mapping distant galaxies, and philosophers pondering the nature of existence. It's what compels us to ask questions that have no easy answers, to push the boundaries of what we know, and to seek connections between seemingly unrelated ideas. Whether it's a child gazing at the stars or a scientist analyzing data from a telescope, curiosity is the spark that ignites discovery. Reflecting on the importance of collaboration reminds us that no single discipline holds all the answers. The universe is too vast, too complex, for any one field to unravel alone. By bringing together the insights of physics, astronomy, mathematics, and philosophy, we not only deepen our understanding of gravity and light, but also enrich our appreciation of the cosmos. It's a reminder that the pursuit of knowledge is a shared journey, one that thrives on diversity, curiosity, and the collective effort of minds working together to illuminate the mysteries of existence. At the heart of every great discovery lies a simple yet profound force, curiosity. It's the spark that ignites our desire to explore, to question, and to seek answers. From the earliest civilizations gazing at the stars to the modern-day scientists probing the edges of black holes, curiosity has been the driving force behind humanity's quest to understand the universe. It's what compels us to look beyond what we know, to push the boundaries of our knowledge, and to dare to imagine the unimaginable. This relentless pursuit of understanding isn't just about solving puzzles, it's about uncovering the deeper truths that shape our existence. Curiosity doesn't just lead us to answers, it also teaches us the value of asking the right questions. When Isaac Newton wondered why an apple fell from a tree, he wasn't just solving a simple problem. He was laying the groundwork for a revolutionary understanding of gravity. Similarly, when Albert Einstein questioned the nature of time and space, he wasn't just challenging existing theories, he was reshaping our entire conception of reality. These moments remind us that curiosity isn't just about finding what we expect. It's about being open to the unexpected, to the possibilities that lie beyond our current understanding. This spirit of inquiry has left an indelible mark on our understanding of the cosmos. The cosmic dance of gravity and light, which we've explored throughout this journey, is a testament to the power of curiosity. Each revelation, from the bending of starlight to the ripples of gravitational waves, has deepened our appreciation for the universe's complexity and beauty. But more than that, it has shown us that the pursuit of knowledge is a never-ending journey. Every answer we uncover leads to new questions, new mysteries, and new opportunities for discovery. As we reflect on the legacy of this cosmic dance, we're reminded that curiosity is more than just a tool for exploration. It's a way of seeing the world. It's about approaching the universe with a sense of wonder, of humility, and of possibility. It's about recognizing that the more we learn, the more we realize how much we have yet to discover. And it's about understanding that the journey of discovery is as important as the destination itself. The story of gravity and light is far from over. With every new observation, every new experiment, we're adding new chapters to this ongoing narrative. And as we continue to explore, we're not just uncovering the secrets of the cosmos, we're also discovering the potential within ourselves. Curiosity is the thread that connects us to the universe, to each other, and to the endless possibilities that lie ahead. It's a reminder that the cosmos is not just a place to study, it's a story to be told, a mystery to be unraveled, and a journey to be embraced. And in that embrace, we find not just answers, but the boundless wonder of existence itself. The legacy of the cosmic dance between gravity and light extends far beyond the stars and galaxies we observe. It's a story that continues to shape the future of science, technology, and humanity itself. Every discovery we make, every mystery we unravel, opens new doors to possibilities that once seemed unimaginable. From the way we navigate our world to the tools we use to heal and communicate, the insights gained from studying these fundamental forces are transforming our lives in profound ways. But this is just the beginning. As we stand on the cusp of new breakthroughs, we're poised to unlock even greater potential, reshaping not only our understanding of the universe, but also the very fabric of our existence. One of the most exciting frontiers lies in the realm of space exploration. Our deepening understanding of gravity and light is paving the way for missions that were once the stuff of science fiction. Imagine spacecraft propelled by light sails, harnessing the momentum of photons to travel vast distances without fuel, or consider the possibility of using gravitational waves as cosmic messengers, allowing us to listen to the universe in ways we never could before. These advancements aren't just about reaching new worlds, they are about redefining what's possible, pushing the boundaries of human ingenuity and ambition. Closer to home, the principles of gravity and light are revolutionizing technology in ways that touch our everyday lives. Take quantum computing, for example. By manipulating particles of light, or photons, researchers are developing computers with unprecedented processing power, capable of solving problems that are currently beyond our reach. Similarly, advances in gravitational wave detection are inspiring new ways to measure and manipulate forces on Earth, from improving earthquake monitoring to enhancing precision in manufacturing. These technologies aren't just abstract concepts, they're tools that could transform industries, economies, and societies. But the impact of this knowledge goes beyond practical applications. It also shapes how we see ourselves and our place in the universe. The more we learn about gravity and light, the more we realize how interconnected everything is, from the tiniest particles to the largest galaxies. This perspective fosters a sense of unity and shared purpose, reminding us that we're all part of a larger story. It's a story that inspires curiosity, creativity, and collaboration, driving us to explore, to innovate, and to dream. As we reflect on this journey of discovery, it's clear that the cosmic dance of gravity and light is far from over. With every new observation, every new experiment, we're adding to a legacy that stretches back centuries and forward into the unknown. The questions we ask today will shape the answers we find tomorrow, guiding us toward a future filled with wonder and possibility. And as we continue to explore, we're not just uncovering the secrets of the universe, we're uncovering the potential within ourselves to dream, to discover, and to shape the world in ways that honor the beauty and complexity of the cosmos. So, as we look to the stars and beyond, let's remember that this journey is not just about science, it's about the human spirit. It's about the courage to ask questions, the resilience to seek answers, and the curiosity to keep exploring, no matter how vast or mysterious the universe may seem. The cosmic dance continues, and with every step, we're not just observers, we're participants, shaping the future with the light of discovery and the gravity of our shared humanity. From the first time early humans gazed up at the night sky, marveling at the shimmering tapestry of stars, to the modern era where we send probes to distant planets and peer into the hearts of galaxies, humanity's journey of exploration has been nothing short of extraordinary. What began as simple curiosity has evolved into a profound quest to understand the universe and our place within it. And at the heart of this journey lie two fundamental forces, gravity and light, that have not only shaped the cosmos, but also our ability to explore it. Gravity, the force that anchors us to Earth, has also been the key to breaking free from it. Without an understanding of gravity, the dream of space travel would have remained just that, a dream. It was Isaac Newton's laws of motion and universal gravitation that first gave us the tools to calculate the trajectories of rockets and satellites. Later, Einstein's theory of general relativity deepened our grasp of gravity, revealing it as the curvature of spacetime itself. This insight didn't just explain the motion of planets, it opened the door to technologies like GPS, which rely on the precise interplay of gravity and time to guide us across the globe. From the launch of the first satellite to the footsteps on the moon, gravity has been our silent partner, both a challenge to overcome and a force to harness. Light, on the other hand, has been our greatest messenger. It carries the stories of distant stars, the birth of galaxies, and the echoes of the Big Bang itself. Telescopes, from Galileo's Hubble instrument to the James Webb Space Telescope, have transformed light into a window to the cosmos. By studying the bending of starlight around massive objects, we've uncovered the hidden architecture of the universe, from the distribution of dark matter to the behavior of black holes. Light doesn't just illuminate the night sky, it illuminates our understanding of the universe's deepest mysteries. Together, gravity and light have expanded our horizons in ways our ancestors could never have imagined. They've allowed us to map the cosmic web, witness the collision of neutron stars, and glimpse the earliest moments of the universe. But perhaps their greatest gift has been the perspective they've given us. By understanding these forces, we've come to see ourselves not as isolated observers, but as active participants in a vast, interconnected cosmos. Every discovery, from the bending of light to the ripples of gravitational waves, reminds us that we are part of something far greater than ourselves. As we reflect on this journey, it's clear that the exploration of gravity and light is more than a scientific endeavor. It's a testament to the power of human curiosity and ingenuity. From the first stargazers to the modern day, explorers probing the edges of the universe, we've pushed the boundaries of what's possible, driven by the desire to understand the forces that shape our reality. And as we continue to explore, we're not just uncovering the secrets of the cosmos, we're writing the next chapter of humanity's story, one discovery at a time. The journey is far from over, and with every step, we're reminded that the universe is not just a place to study, it's a place to dream, to wonder, and